Have you ever stopped to wonder how batteries work? These ubiquitous powerhouses are integral to our daily lives, yet their inner workings remain a mystery to many. A battery, in its simplest form, is a device that stores energy and releases it as electricity. From the remote control you use to switch channels on your television, to the smartphone you incessantly scroll through, batteries are the unsung heroes powering our modern world. Batteries have a rich history that dates back over 2,000 years. The first rudimentary battery, known as the Baghdad battery, was believed to have been created in ancient Mesopotamia. It consisted of a clay jar, a copper tube, and an iron rod, a far cry from the sophisticated energy storage devices we're familiar with today. Fast forward to the 18th century, and we encounter Italian scientist Alessandro Volta, the man credited with inventing the modern battery. Volta discovered that certain fluids would generate electricity when they came into contact with two different metals. He stacked alternating layers of zinc, blotting paper soaked in salt water, and silver to create what is now known as a voltaic pile, the first true battery. In the present day, we have a plethora of battery types at our disposal, each tailored for specific uses. Alkaline batteries, for instance, are commonly found in toys and remote controls, while lithium-ion batteries power our laptops and smartphones. Car batteries, on the other hand, are lead-acid batteries, designed to provide the high current required to start an engine. Despite their different forms and functions, all batteries share a common purpose: to store energy and deliver it when needed. They transform chemical energy into electrical energy, a process that involves complex reactions and the flow of electrons. So, the next time you flick on a flashlight or power up your game console, spare a thought for the humble battery. It's not just a simple object tucked away in a device. It's a marvel of science and engineering. Batteries are more than just objects. They are the lifeblood of our modern, tech-filled lives. But what makes up a battery? What's inside that small, often cylindrical object that powers your devices? A battery, in its simplest form, is comprised of three key components: the anode, the cathode, and the electrolyte. Each of these components plays a crucial role in the function and performance of the battery. Let's start with the anode. The anode, also known as the negative terminal, is where the action begins. This is where the battery stores its potential energy, waiting to be unleashed. The anode is typically made of a material that likes to give up electrons, such as lithium in a lithium-ion battery. Next, we have the cathode, or the positive terminal. The cathode's role is to accept the electrons that the anode is so eager to give away. It's usually composed of a material that loves to scoop up those free electrons, like cobalt dioxide in a lithium-ion battery. And finally, the unsung hero of the battery, the electrolyte. The electrolyte is a medium that allows for the flow of electric charge between the cathode and anode. It's the electrolyte's job to facilitate the movement of ions from the anode to the cathode, creating an electric current. The electrolyte is often a liquid, but it can also be a solid or gel. But how do these components interact? When a battery is connected to a device, the anode starts to release electrons. These electrons can't travel through the electrolyte to the cathode, so they take a detour through the circuit, powering your device along the way. Meanwhile, the electrolyte allows ions to flow from the anode to the cathode, maintaining a balance of charge within the battery. So, there you have it. The anode, cathode, and electrolyte, three critical components that come together to make a battery work. The anode gives up electrons, the cathode accepts them, and the electrolyte facilitates this exchange, all to create a flow of electricity that powers your devices. These three components, when working together, create the energy that powers your devices. The real magic of batteries lies in their chemical reactions. Now let's take a deeper look into this magical world of chemical reactions that make batteries the powerful energy sources they are. In the heart of a battery, there are two crucial players: the anode and the cathode. The anode, often made of lithium, is the negative side, while the cathode, typically a lithium metal oxide, is the positive side. These two are separated by a chemical compound known as the electrolyte. Now, imagine a bustling city during rush hour. That's what's happening inside a battery when it's in use. The anode is like a busy terminal with commuters, in this case electrons, eager to get to the other side. The electrolyte is like a strict security guard, allowing only ions to pass and blocking electrons. This forces the electrons to take a detour, flowing out of the battery and into the device it's powering. This flow of electrons is what we call electricity. Meanwhile, the ions, having made it past the electrolyte, meet up with the electrons at the cathode. This reunion triggers a chemical reaction that creates energy. So, in essence, a battery works by transforming chemical energy into electrical energy. But the magic doesn't stop there. What's fascinating about batteries is that this process is reversible. When a battery is recharged, an external power source pushes the electrons back to the anode, and the whole process starts all over again. However, every magic trick has its limits. Over time, the materials inside the battery degrade, leading to a decrease in its capacity to hold a charge. That's why after a certain number of charge and discharge cycles, batteries eventually wear out. So there you have it. At its core, a battery is a bustling city of ions and electrons, a dance of chemical reactions that light up our devices and power our world. In essence, a battery is a tiny portable chemical plant. Ever wondered how your battery drains and then refuels when you plug it in? Well, sit tight because we're about to dive into the nitty-gritty of the discharge and recharge process of batteries. It's all about the flow of electrons, and it's simpler than you might think. Let's start with discharging. When you switch on your device, a circuit is completed. The battery's job is to push electrons through this circuit. The chemical reaction inside the battery wants to move the electrons from the positive end to the negative end of the battery. When the circuit is closed, these electrons can move and power your device. This is how energy is discharged from the battery. Now, what happens when your battery runs low? The chemical reactions in the battery have used up most of the reactants, so fewer electrons are available to move and power your device. That's when you see the dreaded low battery alert. But fear not. This is where recharging comes in. When you plug in your device to recharge, you're essentially reversing the chemical reactions that occurred during discharge. Instead of electrons moving from the positive end to the negative end, they're forced to move in the opposite direction. This is done by applying an external power source, which provides the energy needed to push the electrons back. The reactants that were used up during discharge are replenished, and the battery is ready to start the process all over again. It's like a never-ending dance of electrons, going back and forth to keep your devices powered up. So there you have it. The discharge and recharge process is a cycle of electron movement, driven by chemical reactions. It's this cycle that allows us to use our devices, then recharge them and use them again. The cycle of discharging and recharging keeps our devices alive and kicking. As technology advances, so does the humble battery. We've come a long way from the primitive voltaic pile, and the journey of the battery is far from over. The future of batteries is a fascinating landscape, filled with potential and exciting possibilities. It's a world where the boundaries of energy storage are continuously being pushed and redefined. Research in battery technology is a hotbed of innovation. Scientists and engineers worldwide are working tirelessly, experimenting with new materials, tweaking designs, and testing novel concepts. It's a relentless pursuit of better capacity, faster charging times, and reduced environmental impact. In the quest for increased capacity, one promising avenue is the development of solid-state batteries. These batteries swap the traditional liquid electrolyte for a solid one, potentially offering higher energy density and improved safety. Imagine a world where your smartphone could last for days on a single charge, or electric cars that can travel hundreds of miles more than they can today. That's the promise of solid-state technology. When it comes to charging speed, the future holds the promise of ultra-fast charging. This is made possible by advances in supercapacitor technology, which could significantly reduce charging times. Imagine plugging in your electric vehicle and having it fully charged in the time it takes to enjoy a cup of coffee. And we cannot forget the environmental aspect. The batteries of the future will not only be more efficient and powerful, but also more sustainable. Research is underway to develop batteries from environmentally friendly materials, and efforts are being made to improve battery recycling. But like all technological advancements, these developments will take time. It's a journey filled with challenges and hurdles. Yet, the potential rewards are immense. As we move forward, the batteries that power our lives will continue to evolve, becoming more efficient, more powerful, and more sustainable. And in this fascinating journey, we are not just passive observers, but active participants. Because every time we charge our devices, we are part of the ongoing story of the battery.